of the methods used to stabilise a rocket in flight and keep it on its trajectory, there's one that most people, I think, are familiar with, and that's the stick on a bottle rocket like this. The stick actually does rather more than merely hold the rocket upright in the bottle or the ramp or the tube that you're firing it from. It actually employs an active principle as a counterbalance weight, actually holding the rocket in a position, balancing the forces of the thrusting head here. We've got a solid fuel, obviously, motor at the front end, and the stick is actually functioning as a counterbalance weight that's being towed behind the lifting body at the front end here. This is the bit I've been looking forward to all day.
A counterbalancing stick is all very well for a firework, but you need a far more active principle with a real rocket. Something that's far more dynamic and able to cope with the changes and aerodynamic movement of wind on the rocket and things like that. It needs to be a principle as dynamic as I'm trying to demonstrate here with this out of balance broom, trying to keep it upright. Just take a look at this V2 archive footage. The V2 is shown hanging in the air over the firing point. Probably because the turbo pump is underrunning. So instead of the motor delivering 25 tons of thrust, it's probably only delivering somewhere between 12 and 13 tons. And the only reason the rocket is climbing at all is because of its use of propellant. But you'll notice that something is keeping the rocket upright as I was trying to keep my broom here.
These gyroscopes are the brains of the rocket. They are in universal mountings. Electrical pickups measure the movements of the gyroscope and translate these movements to the carbon vanes and the trimmers in the tail unit. These vanes and trimmers direct the rocket, both in bearing and elevation, along its trajectory and prevent any deviation from its planned course. The 4 vanes are in the jet of the rocket, and there is a trimmer on each of the 4 fins. This mock-up represents the inside of the control compartment in the rocket. In the background is a skeleton tail unit, with the vanes and trimmers in position. As the control compartment moves, the gyroscopes move in their mountings, and these movements are conveyed through electric cables in the rocket to corresponding servo motors in the tail unit. There is a servo motor for each carbon vane and trimmer. The servo motors move the vanes and the trimmers to counteract the original movement of the control compartment and to keep the rocket on its course. This gyroscope controls the elevation of the rocket by moving a pair of the carbon vanes, thus turning the rocket from the vertical over to an angle of 43 degrees. The other gyroscope controls the direction of the rocket by the movement of this pair of vanes.
Let's take a closer look then at a real gyro platform from a rocket. Here's one from the German V2 ballistic missile. It's fairly well laid out here. One of the great things about looking at the V2 is we get this very basic, very simple design of the gyro platform that really lets us see what's going on. We've got two gyroscopes side by side here with their axes at 90 degrees to one another. We can see the gimbal mount here that the gyroscope rotor is in. We see the gyroscope rotor with its casing there. Other little detail to pick up is this little stud in the centre. There's a little platform with a little stud on it. If we look over at this one over here, we can see a lead weight has been attached to that, almost certainly as part of the assembly process, actually getting the gyroscope in trim and in perfect balance. We can also see there's a little stud there and another one over here, almost certainly used for adding tiny weights to that to actually get it into balance. Another little detail I want you to notice is this assembly on the end of the gimbal here. This is actually a potentiometer. It's like a volume control of a radio, and this is actually used to determine the position of the gimbal when it's in motion. So let's try to get an understanding of the properties of the gyro that can be harnessed to actually control and guide the rocket. And to do that, we're actually going to look at a rather popular toy. I'm not sure if a gyroscope is still a popular toy. Maybe in the age we're in now, maybe this kind of simple thing isn't quite so popular as it used to be. But my brother had one of these, and I used to enjoy playing with it when he wasn't around. And I'm just going to show you some of its properties and see if we can pick up some of an idea of why this device might be able to control a rocket. Just going to give the string a good pull, get the rotor going. There's the first thing it seems to be able to do really rather well is balance itself. I'm going to take it off here and put it on its little stand. You notice as I move that around, I can even pick that up. How about that? Whoops, almost knocked it off. And while that's just running, I'm just going to set up another little demo here. I've rigged a little tightrope here, and we're going to make the gyro go on that. There we go. Right, let's just pick it off there and very gently slow it down, and we'll just put the cord back onto it again. One little trick here with the gyro, if you want to get maximum speed out of it, is to pay the cord onto the axle all the way along, and then very gently play it back again so that it's covering the smallest diameter shaft, so that when we give it a pull we get the fastest speed out of it. Okay, I've got that wound on there now nicely. Just want to show you the little notch at the end there. You can see there's really very little retention actually going on in the notch at the tip there, and we can see I've got the tightrope here all nice and tight and ready to go. Okay, so we're now going to give that a good pull and get the rotor going as fast as I can. There we go. And now I'm going to put the notch straight on there. There you go. How about that? I can even kind of wiggle that around, and the gyro does a pretty good job of stabilizing itself. It's a very good demonstration of the preservation of angular momentum. It's beginning to precess a little bit now. Okay, there we go. We overdid it a little bit, but never mind. We've seen some nice party pieces there from the showing you the power of the gyro, but I still don't think it's absolutely obvious what it is about the gyro that's going to allow us to control a vehicle like a rocket. So I'm going to try to show you now by building a little mechanism. We're going to be doing a little bit of sort of meccano engineering now. Actually show you what it is about the gyro that's going to let us actually control a rocket with it. I'm just going to cut some strips of this up, so bear with me a minute while I build this little mechanism. Just talk amongst yourselves for a second or two. Okay, so there's what we've made, and it's a gimbal unit, so that I can now put the gyro into that inner gimbal frame. It's not exactly a wonderful piece of engineering. It's not really going to win me any prizes, I don't think, but I think it will do for our purposes. I've just got to sort of squeeze that together. Okay, you can see I may have to make some little. Actually, it's not that bad. It's not really in very good balance, and obviously it's not going to be a wonderful demonstration, I don't think, but I think you get the idea. The gyro is now free to move at any angle, and this is going to give us a much better chance to show you one of the principles of the gyro that really weren't shown by those other demonstrations, and it's the key one that's actually used for guiding a rocket in its trajectory and travel. Got plenty of rotation on there. There it is, operating. Now watch what happens as I move it around. Can you see that the gyro is actually retaining its position in space. It'll start to be overcome by the friction of the bearings as I move it around. It won't be quite so happy, and it will start to creep off and it will start to precess. But you should be able to see there that the gyro is actually fighting this. And we can sort of, there you go, it's gone into gimbal lock there. Did it again. Okay. Now, using that principle of the gyro holding itself, in fact, you get a very interesting effect if we try to actually tap this backwards and forwards. You can see there's a very peculiar kind of motion being induced in the gyro as I try to do that, as I try to turn it around. Now, using this ability of the gyro to resist movement of its position, all we've got to do is introduce some method of measuring the change of angle between the gimbal frame here and the architecture of the metalwork that's actually holding it. Let's call that the rocket body itself. Now I'm going to do that by adding a little scale. It's really just to show you a principle, and I'm going to stick that on the end of the side of the gimbal frame here next to one of the axes. Put that in position, and then I'm going to put a little indicator on the axle that's actually holding the inner gimbal, and you can see now. So now I've got the means of making a measurement as that moves, and I'm just going to lace it up again. Let's just get it going quickly as we can now. I'll set it in a, I haven't even got it in a way that you can actually see it. Whoops, where are we? Now as I move it around, you can see the gyro trying to stay steady there, and we can now read off on the scale here the changes between one frame of reference and the other frame of reference set by the inner gimbal. Now obviously, if we then, instead of having this very simple crude paper guide on here, I'm just going to stop the rotor. If at this point we put a variable resistor, like the one I showed you earlier, the potentiometer on the V2 gyroscope, we can put a voltage across that and actually measure that change, that angle that we're showing you there. And then by sending that signal measured by the variable resistor to an amplifier, we can then send a control current to the jet vanes on the rocket and obviously make a corrective action of the angle of the rocket, so that the position of the fixed frame of reference can be brought back to the indication given by the gyroscope. What I'm going to do now is just show you a couple of bits of real gyroscopes. These ones are from the early days of research at Peenemünde. What we're looking at here is an air gyro rotor. So this part here corresponds to the part in the centre of the gyro that spins round. And if you get a close-up view of that, Andrew, we can actually see the air buckets that we use to drive this one. In actual fact, the gyros on the production V2s were actually electric in character, but this one that we see here from the early days of their research is actually air driven. This is a more modern one. This is a rotor out of probably an artificial horizon from an aircraft, and you can see that same air bucket pattern there on the modern rotor. You can also see some little details like these holes that have been drilled in the edge of the rotor to actually balance it up, and you can see there's exactly the same thing on the modern rotor here. That's those ones. This is the same rotor again, but this time with the air casing actually around it. This is another gyroscope from a V2. This is actually from a pendulating, integrating gyroscope for measuring the velocity of the rocket on its trajectory. But finally, we'll just sum up by showing you a more modern gyroscope. This gyroscope has actually been removed from a Soviet-era ground-to-air missile, the SA-75, and one of the things to note about it is the balancing again of the system. If I can just spin that around. Obviously it doesn't look very much like the child's toy now. It looks a lot more sophisticated as well than the one we were looking at on the V2, but that now gives you an idea. You've seen how the principle of the gyroscope with its preservation of angular momentum can actually be used once it's harnessed in a gimbal structure like this to send control codes to a steering mechanism of a rocket. Anyway, that's it for now. We'll see you again soon.